Hi, everyone. Thank you for coming today. It's my great pleasure to introduce one of the great minds of our time, Murray Gell-Mann. Professor Gell-Mann has a list of accomplishments so long that I could spend all hour up here reciting them. I won't do that, but I'll highlight a few. He's been recognized by the Atomic Energy Commission, the Franklin Institute, the National Academy of Sciences, the United Nations. He has honorary degrees from, well, more institutions than most of us have even attended. And then there's that little prize he won in 1969, the Nobel Prize. He's spent his life contributing to our understanding of the world and the universe. Today, he's here to deliver a talk on getting creative ideas. So please join me in welcoming Professor Gell-Mann.
Well, I'm very pleased to be here and to talk with you about this subject. Probably most of you have heard most of the things that I'll refer to, but maybe for each of you there'll be a little nugget that's new. I hope so. The notion of a creative idea can be extended from science to art and business and many other activities in which we engage. And whenever a comparison is made among the different kinds of applications, it seems that there are very close parallels. I was part of a group that met in Aspen in 1969 to talk about the experience of getting a creative idea, the light bulb turning on, the aha moment. And there was a poet, two painters, a theoretical biologist, and I was the theoretical physicist. There was another visual artist, a very famous one, but he didn't stay. He couldn't stand listening to anyone else talk, and he went out and got drunk instead of staying. That doesn't stop me from collecting his prints. Anyway, all of us who spoke had very similar experiences. There was a contradiction between certain established or available ways of doing things and something we needed to accomplish. In art, the expression of a feeling, a thought, an insight. In theoretical science, the explanation of some observations. Well, first of all, each of us worked for days or weeks or months to resolve this contradiction between what was needed and what we had, filling the mind with the problem. Then, second, there came a time when further conscious thought seemed to be useless. But somehow, outside of conscious awareness, mental activity went on anyway, or at least that's my interpretation of what happened. Third, one day, while cycling or cooking or shaving, or by a slip of the tongue while talking, or even while sleeping and dreaming, according to some people, the crucial idea turned up that got us out of the rut and resolved the contradiction. All of us at that meeting were impressed with the congruence of our stories. I discovered later by reading that none of this was new. The great German scientist Helmholtz in the late 19th century had already described 3 steps and named them saturation, incubation, and illumination, just corresponding to what we were discussing. Henri Poincaré, the great mathematician, in 1908 added a 4th step, obvious but also crucial, verification. Check that the idea works. It turned out that the psychologist Graham Wallas, in his text in 1926, had already listed these 4 steps, but none of us knew about it. None of us had read his book. We just came across the same ideas through personal experience, these 4 stages. In theoretical science, a new idea may permit us to alter or extend the body of theory to explain observations that previously couldn't be understood, and, of course, to make new predictions that can someday be verified. Let me give an example from my own experience. In fact, I'll give a little later another example from my own experience. But this one is earlier, 1952. So-called strange particles had been observed in the cosmic radiation. Later on, they were observed also in accelerators when the more energetic accelerators went online. Some of us were trying to explain why these strange particles took so long to disintegrate into other particles when they were made copiously. If they were made copiously, they must have interacted strongly. But if they took a long time to decay, as much as 1/10,000,000th of a second, which in particle physics is a very long time, they take a very long time to decay, they must be weakly coupled. So what was going on? Well, I thought I had succeeded in explaining the strange behavior of the strange particles. Let's take, for example, a proton, a particle similar to the neutron and proton, which was strange. It was produced copiously, but took a long time to decay. My attempt at explanation involved a quantity I, isotopic spin. I can have values 0 or 1/2 or 1 or 3/2, whatever. The conventional wisdom was that particles like the neutron and proton, which have spin angular momentum 1/2, j equal 1/2, had to have I equal 1/2 or 3/2 or 5/2, but not an integer, not a whole number. Other particles, mesons, with spin angular momentum j equals 0, would have I equals 0 or 1 or 2 or something. There would be this similarity between the values of I and the values of j. It was a very nice idea, but there was no reason for it. I visited the Institute for Advanced Study, where I had spent the previous year. And people had heard that I had had an idea to explain the strange behavior of a particular particle. And, but then I realized that it wouldn't work. I thought I had, by assigning the value I equal 5/2 to this particle, that would prevent it from disintegrating by means of the strong interaction into two particles with I equal 1/2 and I equal 1. Because with 1/2 and 1, you can't seem to make 5/2. However, it turned out that electromagnetism can change this value of I by a half unit. And electromagnetism isn't all that weak. So the idea failed. And the people at the Princeton Institute for Advanced Study had heard that I'd had an idea, but that it hadn't worked. And they asked me to explain the idea and why it was wrong. Well, I got up to do so, and I said what I've been saying here. And when I got to this idea of assigning to the new particle I equal 5/2, so it couldn't decay into 1 and 1/2, I made a mistake, a slip of the tongue. I said I equal 1 instead of I equal 5/2. I said, let's assign this particle I equal 1. And then I stopped dead, because electromagnetism isn't going to change I by a half unit. So if it really had I equal 1, that would solve the problem. But everybody thought that this particle had to have half-integral values of I. Well, I quickly reviewed in my mind what could be the reason for this prohibition. And I realized there wasn't any reason. It was just something that people told one another. It didn't take long. It just took half a minute or something for me to realize that there was no reason for this rule. And I could freely violate it. So the rest of the seminar was quite different from what was anticipated. Here it is written down on a transparency. Well, we can go over to much more important realm in elementary particle physics, or in fundamental physics, I should say, and that is the work of Einstein. Now, we all know what kind of techniques he used for getting his ideas. They are described in numerous cartoons. This is one of them. When he proposed special relativity in 1905, he had to get rid of the requirement of absolute space and time. Ever since Newton's day, everybody knew that there was absolute space and absolute time. And here, Einstein was dealing with space and time which transformed into each other to some extent, depending on the state of motion of an observer. If you run rapidly past the system, what was previously x becomes x and a little bit of, becomes mostly x and a little bit of t, and t turns into mostly t and a little bit of x, where t is time and x is distance. So he was dealing with relative space and time, not absolute space and time. But everybody knew that there was absolute space and time. He said, well, everybody may know it, but we don't need it. Throw it away. And he was quite right. Another modest example from my own experience, proposing quarks as fundamental constituents of neutrons and protons. People are always asking me why I chose that name, but if you think about the sound, it's an obvious name for fundamental constituent of atomic nuclei. Well, that wasn't the problem. The problem was that I was violating several rules, things that everybody knew. Everybody knew that you don't have objects that are permanently stuck inside observable objects and can never come out to be detected singly. But quarks are like that. They're permanently stuck inside particles like the neutron and proton, which they compose, and they can't get out singly. That's why there isn't another Route 125 around Boston, 128 around Boston, with quarkonics industries. If the quarks could escape singly, they would have all sorts of practical uses in industry. But they can't. They're stuck inside. However, the idea of particles being permanently stuck inside was not a familiar one, and most physicists thought it was impossible. Just the very fact that the neutrons and protons are composite and made up of simpler things was also not orthodox belief. They were supposed to be elementary. Everybody knew they were elementary. Third, the electric charges of particles were supposed to be integral multiples of the proton charge. So 0, 1, minus 1. The quarks, however, have plus 2/3 and minus 1/3. Well, that's obviously wrong because everybody knows you don't have fractional charges. However, despite all these prohibitions, despite violating all these prohibitions, it turned out that the idea of quarks was quite correct. And was verified not very far from here at SLAC on Sand Hill Road, where my friends, Dick Taylor, Henry Kendall, and Jerry Friedman, took what amounts to an electron microscope picture of the proton. And they were able to deduce from that it was actually made of, mostly of 3 quarks. Now, we mustn't get the idea that any challenge to scientific orthodoxy is likely to be right. Quite the opposite is true. Most challenges to scientific orthodoxy are wrong, and very many of them are crank. One has to verify, if challenging some accepted idea, that it really can be dropped. I've talked in these last few minutes about certain ideas that could be dropped, but not everyone can be. You should always ask why not, but realize that usually there's a damn good reason why not. A few years ago, I was asked by a huge company to appear in their television ad on the theme, why not? I didn't have to say anything good about the company. I just had to say something about asking why not. I appeared for just a moment, but they paid me a reasonable fee for it. And next year, they were very pleased. The following year, they were very pleased with the reception of the ad. And they ran it again, which means, according to the rules of Actors' Equity, that I got the fee again and a second year's membership in the Screen Actors Guild. Then they invited me to come to their headquarters and speak to the management and also through their intranet to all their employees around the world, at least in suitable time zones. All on the same subject, asking why not. And I emphasize that it's a very productive idea to keep asking why not, but that in science, there's usually a very good reason why not. I said, I don't know much about business, but I assume it's similar in business, that you should always ask yourself why not about all sorts of ideas, all sorts of proposed changes, but realize that is generally a very good reason why not. You have to watch out always for certain things, I said. One of them is profit and loss. Even though I'm not a businessman, I assume that profit and loss are important. Also, legal and ethical considerations. Well, they should have taken notes. It was, of course, Enron. Fortunately, the fees were not paid in stock. Now, I mentioned that there were artists at that meeting in Aspen. What about art? Well, for the visual arts, we can pay attention to the late Kirk Varnedoe, a splendid guy who was the longtime head of painting and sculpture at the Museum of Modern Art in New York. He wrote a book, which I recommend, called A Fine Disregard: What Makes Modern Art Modern? And his idea is that in modern art, and also contemporary art, which is still more recent, the artist plays with the rules instead of always playing by the rules. The title of his book, A Fine Disregard, comes from the inscription on a stone next to a playing field at Rugby School in England. Kirk Varnedoe was a former rugby player, and he was very interested in that commemorative stone at Rugby School. Here's what was written on it, what's still written on it. This stone commemorates the exploit of William Webb Ellis, who, with a fine disregard for the rules of football as it played in his time, first took the ball in his arms and ran with it, thus originating the distinctive feature of the rugby game. AD 1823. So what we're talking about in this connection is problem formulation rather than problem solution. And I believe that problem formulation is usually much more important than problem solving, and in many cases more difficult. It doesn't look more difficult, but it turns out to be harder in some ways, in many cases. You have to ask, what are the real requirements in this situation? What are the real conditions that the solution must satisfy? If you get that right, then you can try and figure out what the solution is. There's one place, however, where the problems are formulated for you: school. It's almost the only place where the problems are formulated for you, and then you just solve them. In almost any other place, in almost any other human activity, the challenge is to formulate the problem and then later solve it. There's a very familiar exercise that all of you have seen that can be made to illustrate this point. Here's the diagram. You've all seen it. 9 dots forming a square. And you're asked to connect all the dots by drawing the smallest possible number of straight lines without taking the pencil off the paper. And anybody can do it with 5 straight lines. It's very easy. To do it with 4 straight lines, which is possible, you have to go do something like this. And you notice that the lines are outside of the square at times. That may be, for all I know, where the expression thinking outside the box comes from. This would be the box, and these lines which connect the dots, if you're going to do it with 4 lines only, get outside the box. And at the Santa Fe Institute, where I work, we have a resident cat. And there's a cartoon posted on the wall that has a man talking to his cat. The cat is on the floor next to a tray of kitty litter. And the man is shaking his finger at the cat and saying, "Never, never think outside the box." Now, if we're going to solve this problem, you can solve it in a trivial way, as we saw, by going outside the box. But you could imagine other things. Besides asking whether you are allowed to draw lines, are you allowed to draw lines that go outside the square? But you can also ask, do you have to treat the dots as points? In the actual picture, they're little round dots. They're not points. They have width. Can you take the width into account? Are you allowed to? Are you allowed to use the thickness of the lines as opposed to mathematical lines, which have no thickness? Are you allowed to crumple up the paper and drive the pencil through? You could do it in 1 line. Which of these is allowed? Which of these are allowed? This exercise and these questions about what's allowed were treated in a somewhat different way from the way I'm treating them, but the same general idea. They're treated in a book by Professor James L. Adams called Conceptual Blockbusting, A Guide to Better Ideas. They're also emphasized in talks by my friend Paul McCready, who developed the bicycle-powered aircraft and the solar-powered aircraft and the flapping pterodactyl and lots of other things. Here's a letter that a 10-year-old girl wrote to Professor Adams. I'll read it to you, but it's also here so you can look at it. Dear Professor James L. Adams, my dad and I were doing puzzles from conceptual blockbusting. We were working mostly on the dot ones, and then she has the 9 dots here. My dad said a man found a way to do it with 1 line. I tried and did it, not with folding. I used a fat line. It doesn't say you can't use a fat line. Like this. Actually, you need a very fat writing apparatus Sincerely, Becky Beagle, age 10. I wonder what happened to Becky Beagle. Another thing we can say about creative ideas with illustrations from physics, but also illustrations from lots of other things, is that often a creative idea involves taking an existing idea and building on it, taking it more seriously than its original proponent did, and using it for some other purpose. We can look again at 1905, that miraculous year for Albert Einstein, when working as a patent clerk in Bern, Switzerland, the capital of Switzerland, he had 3 ideas that he published in the same volume of the German physics journal, Annalen der Physik. Not only the same year, but the same volume of the journal. Special relativity is one, and we mentioned it. But we didn't mention this interpretation of it. One way to describe special relativity is to say that the symmetries, the transformations of special relativity are the symmetries of Maxwell's equations for the electromagnetic field. And what Einstein did was to take those symmetries, the symmetries of Maxwell's equations, and apply them also to particle dynamics, to the particles moving in the electric and magnetic fields of Maxwell, so that the whole problem obeyed these symmetries. And the symmetries are the symmetries of special relativity. They're just the space-time transformations of special relativity. Now, those transformations were known already, especially to the Dutch physicist H.A. Lorentz. Lorentz found these transformations, exactly the same ones that Einstein used later for special relativity, and to this day they're called the Lorentz transformations. Well, why isn't special relativity attributed to Lorentz? Well, 2 things. We've seen already that Einstein threw away absolute space and time and left only the relative space and time of relativity. Lorentz didn't do that. He kept looking for a way to fit absolute space and time in with the relative space and time, and of course he never found it. Einstein simply took the step of cutting the Gordian knot, throwing away absolute space and time. But there's another reason. Lorentz didn't take the additional step of applying these same symmetries to particle dynamics. They remain just the symmetries of Maxwell's equations for electromagnetism. It took Einstein to add the additional idea that these transformations were general and they applied to the particle dynamics as well as to the electromagnetic fields. So Lorentz was a great man and did very important work here, but he failed to see these two important points. And so Einstein was taking Lorentz's idea more seriously than Lorentz himself had. That's even more obvious and even more striking in the case of Einstein's work on the photoelectric effect. In the photoelectric effect, a bit of light hits a metal surface and knocks out an electron. And Max Planck in 1900 suggested the quantum, that for this purpose, electromagnetic energy came in packets of energy, where the energy was Planck's constant h times the frequency of the light, or of the electromagnetic wave. Well, this was a rather revolutionary idea, but Planck didn't carry it far enough. He had the idea of the quantum, all right, but not in connection with the photoelectric effect. It didn't occur to him that electromagnetism, in hitting the electron and knocking it out, would come in the form of a quantum. If you do assume the quantum in that case, you get this simple equation of conservation of energy. H nu is the frequency, h is Planck's constant. This is the energy of the quantum. The energy of the quantum equals the electron's kinetic energy plus the energy necessary to knock it out of the metal. Very, very simple equation. But this equation worked. It explained the data. The data conformed exactly to this equation. Planck didn't like it. He had invented the quantum for other reasons. He believed in the quantum for these other purposes. But taking it more seriously than he had originally done was not something he believed. He didn't think that Einstein understood what he was doing in applying the quantum to the photoelectric effect. Nevertheless, Planck looked favorably on young Einstein. He recommended him for membership in the Prussian Academy of Sciences, which was a rather high honor, and eventually for the Swedish medal, the Nobel Prize, which Einstein didn't win for another 16 years. And he got it for the photoelectric effect. Finally, people stopped objecting. Even Planck, I guess, stopped objecting eventually to his use of the quantum in this connection. Planck said, well, earlier on, Planck said, well, Einstein is really very good. He's a very good physicist. We'll forgive him this youthful indiscretion of believing that the quantum can be used here in the photoelectric effect. But finally, in 1921, he won the Nobel Prize for it, just for this equation. A third thing that Einstein did in 1905 was to study the Brownian motion. You know what that is. It's discovered by the English botanist Brown around 1830 or so. You can see it yourself if you look at something like ink in water under a microscope. You see the little particles of ink moving randomly in little jerks. And Einstein and also the Polish theorist Smoluchowski, at the same time, suggested that they were being hit by molecules. And Einstein worked it all out mathematically and figured out how many molecules per unit volume you would get in a gas and compared it with other estimates of that and measurements. And it all seemed to work. And Smoluchowski did something similar. What they were doing was taking seriously the notion of a molecule. Everybody agreed that molecules were useful in chemistry, a sort of chemical bookkeeping, but that the molecule was something that could hit you, that could hit an ink particle and make it move. That was not believed by most physicists. But this work made it clear that the molecule was a real thing that should be taken more seriously than it had been taken by people who suggested it earlier. Now, let me close by discussing very briefly the notion of teaching creative thinking. There's nothing to tell us a priori that it's impossible to improve creative thinking by teaching. It might work, it might not. The proof would have to be in the pudding. One man who has ideas about that and tries to teach creative thinking does so very widely in many large corporations and so on, is Edward de Bono. And his kind of reasoning can be represented this way. He doesn't say exactly this, but this is something that relates to the way he looks at things. You imagine that you have a landscape of ideas looking like this, with shallow holes and deep holes. And the deep hole is a great idea that you should get eventually. The shallow holes are less good ideas that will not solve your problems. And the objective should be to get somehow to the bottom of this deep hole and stay there. Now, if you're just moving downhill, if your only instruction is to keep moving downhill because you think a better idea lies in a certain direction, then you're likely to get stuck in a shallow hole, because there are lots more shallow holes than deep ones. However, if you have noise or heat or simulated annealing, as it's often called, so that there's a random motion superposed on going downhill, then if it's the right amount of heat or randomness, you could be knocked out of all the shallow holes, but not be knocked out of a deep one because of the tuning the amount of heat or noise or whatever it is you're adding to the system, so that it's enough to knock you out of shallow holes, but not enough to knock you out of a deep one. Then looking for the right idea would involve a tendency to move downwards, modulated by some noise that knocks you out of shallow holes but still allows you to explore the deep one. So that suggests, if there's anything to it, it suggests that you should apply that if you're trying to solve problems. You should try to use something random in addition to all the logical, rational, reasonable inputs to your thinking. You should use something random. So what Edward suggests is looking at the last noun on the front page of today's newspaper and using that to solve your problem. That contributes enough noise that maybe you'll be thrown out of the shallow holes, but perhaps you'll be able to reach a deep one and stay there. We shouldn't think that finding creative ideas is restricted to these stratospheric realms of science and art and so on. It can also appear at any moment in everyday life. We're all faced with little puzzles every day. And the more we have all this equipment in our lives, the more it's true. At any moment, we can be faced with something that requires a creative thought. One writer on this subject discusses the case of a company picnic involving a lot of cheese. No one, however, is thought to bring a knife to cut the cheese. But a young lady pulls out her credit card and cuts the cheese. That's a much more modest achievement than many of the things we've been talking about, like special relativity and so on. But it does involve a creative idea, and it involves using something beyond the domain for which it was originally proposed. Well, I'm very happy to answer questions, and I regard this little talk as just as an introduction to a question and answer session. Thank you.
Well, thank you for joining us. I guess I have a couple things to say. One of them is that I'm not sure how familiar you are with computer science, but it isn't obvious to me whether it's yet a science, except for when it comes to debugging. And I'm sure that when we're debugging, we are doing science. And people talk about the creative process in science as coming up with models or, explanations. But at least in my observation, there's two other steps that are highly creative in the scientific method. And one of them is coming up with a specific hypothesis to test. And the third is coming up with a test for it.
Yes, well, I included those as well. I said that in science, you may be accounting for some new data, or you may be proposing a new hypothesis, or you may be suggesting a prediction, making a prediction that would allow a hypothesis to be tested. I agree with you completely. I actually said it.
Thanks.
You're completely right. That's theoretical science.
Yeah.
There's also experimental science, and there's also the making of equipment. And all of those involve lots of creative thinking. It's just that I was talking about theoretical science.
Yeah, I'm not complaining. I just wanted to sort of emphasize these areas that I think get underemphasized in discussions.
Yes, you're quite right.
Thanks very much for the talk. I'm an avid amateur observer of particle physics and particle physicists without being very mathematical. And I wondered if you had any thoughts on string theory and string theorists who seem to have lots of ideas but very little experimental evidence so far.
Well, let's see. I'm asked that question often. I am a an important patron of superstring theory. When superstring theory was first developed, 1971, 72, I thought that it would be very important. I didn't know for what. And I asked the people who were doing it to come to Caltech to join my group, especially John Schwartz and Pierre Ramon. André Neveu, who wrote the original paper with John Schwartz, came for a while, but then he returned to France. But the other two stayed. And we gradually built up quite a group at Caltech, part of my theoretical particle physics group. So most of the work, a great deal of the work anyway, that was done on superstring theory between 72 and 84 was done in my shop. Not by me, but people who came there. And during that time, we realized that what the use was, what the possible use was of superstring theory. It was originally intended to be a theory just of the strong interaction, the hadrons, so-called, strongly interacting particles. But it was discovered that it couldn't be a theory of the strongly interacting particles because it had a particle with 0 mass and spin 2, which you couldn't possibly have in a theory of the strong interactions. There's no meson like that. But there is a particle like that, the graviton, quantized gravitation. So what this was a candidate for a theory of all the interactions, including gravitation. And it was noticed in the middle 70s that a theory based on superstrings would predict Einstein's general relativistic theory of gravitation. And it would predict it within quantum mechanics. And without the crazy infinite corrections which appeared in other attempts to unify general relativity and quantum mechanics. That is what, in my opinion, made it very attractive. It had the graviton, of course, which made it unsuitable to be a theory of the strong interaction, but very suitable to lead, perhaps, to a unified theory of all the forces and all the elementary particles. Well, since then, it's 30 years or so, people have been trying to build a correct unified theory, or a good candidate for a unified theory based on superstrings. And they've made an enormous amount of progress in various spurts. They haven't got there yet, however. And some of the efforts look discouraging. Some of the results of some of the efforts look discouraging, but in other cases, not so discouraging. As to predictions, there will certainly be predictions. We've already seen a retrodiction of very great importance, namely the retrodiction of Einstein's general relativistic theory of gravitation. This is not negligible. There's also the prediction that you have supersymmetry, presumably broken supersymmetry, since we don't observe exact supersymmetry. Supersymmetry is a symmetry between fermions and bosons, between particles that obey the exclusion principle, like the electron, and particles that obey an anti-exclusion principle, like the photons. That anti-exclusion principle is what makes the laser possible, of course. Photons love to be in the same state at the same time, and that's how you can have a laser beam. The supersymmetry has to be broken to be compatible with observation, and it has to supply for every elementary particle a companion with the opposite statistics. In other words, for every elementary fermion, there has to be a boson, and for every elementary boson, there has to be a fermion. And these have received some peculiar names. I was there when they were named, but I didn't name them myself. The selectron for the electron, the photino accompanies the photon, and so on and so on. Now, these things are being sought at accelerators. When the new, bigger accelerator comes online near Geneva, next year or the year after, they'll really step up the search for these partners, super partners of the known particles. And if some of them are found, that will certainly be encouraging for theories based on superstrings. Supersymmetry, broken supersymmetry, is also very good for answering a number of other theoretical problems that we have. But you could, of course, technically have broken supersymmetry without having superstrings. So enemies of superstrings, who seem to have turned up in various places, can always say that. But I think that finding superpartners will be very encouraging for the possibility that one can construct a suitable superstring theory based on superstrings. But attacking a theory that hasn't yet been constructed is a little strange. I think mostly it's about money. Some people would like some of the money that goes to the smart people who work on superstring theory to go to them.
Thanks
Maybe they're right, I don't know.
Thank you again for coming. I have a more general question, which is on the theme of creativity. You've described...
I didn't talk about creativity. I talked about creative thinking.
Creative thinking. Well, I won't argue the
I think of as
difference.
something else. It's some sort of probably inborn characteristic that allows you to engage in creative thinking and in creative projects in science and art and so on.
Okay, so I'll restrict myself to creative thinking then. But the examples you've given of creative thinking are, I'll say, directed once you have found the problem. There is a chunk of cheese that needs to be cut, or there's an unexplained spin that needs to be explained. And so you already have the problem there. And I'm just wondering if you have, and there is a question of how do you think outside the box, for example, to attack that existing problem? But as you pointed out, there's this issue of, as engineers, we often have the problem in front of us. There's something that's not running, or there's something that's not running well enough. But there's also we find ourselves in this situation of looking for a problem to solve. Okay, everything's cleared from my desk. I'm an engineer, I'm a scientist, I'm an artist. How do I decide, can we apply creative thinking to figuring out, since we're not in school and the problems aren't necessarily given to us, can we apply that same or some similar heuristics to figuring out what problems we should be attacking next?
Well, that was the subject of my talk, really.
Well,
I said that problem formulation is usually much more important and in some sense, not an obvious sense, but in some sense more difficult than problem solution.
right.
You have to find out what's wrong. You have to, where is it itching so I can scratch it? And that's tricky sometimes. What rules do I have to obey in order to get something, in order for me to be allowed to have something new? What rules do I have to violate? What rules can I violate without running into a contradiction or running into a contradiction with nature? And so on and so forth. So it's precisely as you say, that you have the most important time is when you are not sure what the problem is. You have a piece of equipment that isn't working, maybe you shouldn't have that kind of equipment.
But when
Maybe you
the
should have a
equipment
completely
is
different
working,
kind of equipment. You're generating energy in some particular way, maybe you should generate it in some other way. Or maybe you shouldn't generate it at all, but save energy. And so on and so forth.
right. But when the equipment isn't working, it's that's sort of a problem. It may suggest an open issue that's completely unrelated to the equipment not working.
Exactly.
But essentially, that's where something is itching. I guess what I'm finding is
Not necessarily. Not necessarily. And even debugging, which was mentioned, is an interesting topic. We all know of a gigantic corporation that does no debugging, that allows the customers to do the debugging. That was an interesting invention. Imagine being able to make money by selling a whole lot of products that don't work and letting your customers figure out how to improve them. It's a great idea.
okay.
It also describes the universe. I wanted to ask you about another creative idea that's about 30 years old and that can potentially change the way we work here. What is your take on the future of quantum computing?
Oh, quantum computing. Well, so far, one hasn't gotten terribly far with it except for a lot of ideas. And the ideas are of two kinds, of course. One is how we might be able to make a quantum computer that works. And the second is what kinds of problems could it solve for us? What kinds of things could be, what sorts of things would be changed by having quantum computers? Well, originally, people thought that it would be very, very, very difficult to maintain the coherence for long enough or over a big enough range to have a functioning quantum computer, but that once you got it, it would be able to solve all sorts of problems in polynomial time, which is thought to require exponential or worse time to solve. Well, it hasn't quite turned out that way. Mr. Shor, of course, found that one famous algorithm involving factoring huge numbers into their prime factors, that could probably be reduced to a problem soluble in polynomial time. But other than that, there hasn't been any proof of that. Instead, people have stopped thinking that it's necessarily so difficult to maintain the coherence because they have all these error-correcting algorithms that might succeed in canceling out the inherent noise in a quantum computer and allow for allow for a situation that would resemble a situation with a lot of coherence. So it's just turned around, as far as I can tell. The ideas about quantum computers have turned around. It's maybe not so difficult to simulate the coherence that you need through all these error-correcting procedures, but it may be difficult to find a problem that the quantum computer will solve better. And people have started thinking, therefore, about quantum systems. What about simulating quantum systems? Quantum computer might be really good for that. And it's quite different from the kind of use that people had in mind some years ago. But so far, the quantum computers are very limited capacity. And as my good friend Seth Lloyd says, a 2-bit computer is a 2-bit computer. We've wondered where our alumni of the Santa Fe Institute would get jobs, and we worried whether they would get jobs at all because they're all highly interdisciplinary. But academic jobs seem to be available, provided you don't try to predict in what department. Some of our physics-trained people have ended up in sociology. One professor at Columbia, who spent a long time at the Santa Fe Institute, a very brilliant guy from Australia, said that the first sociology class he was ever in was the one he was teaching as a full professor. So Seth Lloyd has become a professor of mechanical engineering. And because he's trying to develop quantum computers, he says he's a professor of quantum mechanical engineering, which satisfies everybody. But he's the one who says that a 2-bit computer is a 2-bit computer. That's all we have so far. I don't think I've answered your question, but
actually, it's his question.
Maybe you could ask again.
No, it's okay.
My question actually sort of ties into that. One focus of creativity would seem to be interdisciplinary and applying things you've learned or approaches from one field to a very different field. And again, speaking as an amateur in physics, it seems like the two things that at least get the most publicity outside the field right now are superstring theory and the whole dark matter, dark energy issue. I never hear anything about how those combine. Is there any sort of combination of those? Or?
Well, let's say what dark matter and dark energy are. They're not very good names, especially dark energy is a really dumb name. Especially because people could mix it up with dark matter, with which it has almost nothing to do. Dark matter refers to the fact that galaxies and clusters of galaxies are made up mostly of different material from what we're accustomed to discussing, not stars and planets and ordinary molecules and so on and so forth, made of something else. And that's called dark matter. And the superpartners of known particles may well make a major contribution to the so-called dark matter. I used to walk by the astronomer's table at the faculty club at Caltech when I was still teaching there. And I would say to them, don't you guys realize you're talking just about 4% of the universe? Everything else is photinos. They didn't like that. However, it was perfectly true. We don't know if it's photinos, but it's something. There may be several kinds of dark matter. Now, dark energy is a really dumb name for the discovery that the recession of galactic clusters, that's called the expansion of the universe, is accelerating. The expansion of the universe, you have to realize, if you're a layperson in this business, doesn't mean that atoms recede from one another, or that rocks recede from one another, or planets and stars recede from one another. It's not even galaxies recede from one another. It's clusters of galaxies, gravitationally closed, that undergo recession from one another. And with the discovery that this recession is accelerated, we're back to the old question of the cosmological term in Einstein's general relativistic equation for gravitation. He introduced this cosmological term because he wanted a static universe. He didn't realize that there was observational evidence for an expanding universe. He wanted a static universe, and since the universe would collapse under gravitation, which is purely attractive, he had to introduce something else that would stabilize it, so he introduced this extra cosmological constant, a single constant added to the equation for gravitation. And then he realized that through the work of Hubble in Pasadena, that the clusters of galaxies were receding from one another, and you had an expanding universe. So he then said, oh, this was a terrible mistake. I've committed this terrible error of introducing this extra term, marring the beauty of my equation. And it's not necessary, because we have an expanding universe, and it will either keep on expanding or eventually contract, and we don't have to worry about this extra term. But now it's back, apparently, or something like it. Either that or something very like it, in order to explain the acceleration of the expansion of the universe. The question is, why does it have the value that it has? The funny thing isn't that it's non-zero. If you look at it in the light of particle physics, there has to be such a term. It's the average energy of the vacuum or something. It's a fairly obvious thing that it must be there. The question is, why is it so tiny? Because if you try to estimate from particle physics what kind of a value you might have for it, the discrepancy between that and what is seen, assuming that what is seen really is a cosmological term, the discrepancy is by a factor of 10 to the 118th, which is the largest fudge factor in the history of physics. And that's a really good question. I would like to know the answer to that.
Thank you.
Thank you so much for coming, Dr. Gell-Mann. I'm curious, having spent a lot of your career in something called theoretical physics, what are the applications of your work that have given you the biggest thrill? Or,
applications?
Yeah, I mean, for instance, the laser, the microwave oven. I mean, are there pieces of technology that we have in the real world that you look at knowing the physics behind them, you look at that and say, wow, that's really neat, and I helped contribute to that?
I can't think of any application. But it takes a while, you know. I mean, I'm very, very, very old now. want to think of me as a child prodigy. I'm a very old child prodigy. Anyway, nevertheless, not old enough to see the applications of the things I worked on. Take the laser, for example. It came out of Bose-Einstein statistics, as I said, the fact that photons like to be in the same state at the same time. And this was proposed theoretically in 1917 and 1920 by Einstein and by the Bengali physicist Bose, or Basu. But it wasn't until 40 years later that we got the laser. And the same kind of time interval may apply to lots of other fundamental ideas and fundamental discoveries, that they don't lead to gadgets until much, much, much later. So now, if the quark had been able to escape singly from its prison, we would have quarkonics for sure. Lots and lots of applications, including mediating thermonuclear fusion. But sorry.
I'm curious. I've noticed that the experimental physics is getting increasingly expensive. For example, at the LHC, where they're building something very large, which may or may not discover like a stop particle.
May not discover what?
The stop, super top.
Oh, I see. Yes.
Sorry. I'm curious what you think about computational approaches like lattice gauge theory or...
Oh, it's very good, of course, but it doesn't substitute completely for experiments. No, at Santa Fe Institute, we do a lot of simulation and modeling and so on with computers, and computer experiments are extremely important, but they're extremely important usually when you have some model or theory of what's going on and you want to understand its consequences. But we also need to know what's actually happening out there.
Thanks again.
We waste a lot more money on a lot of other things. I wouldn't worry about wasting money on particle accelerators. If there's another one, it will be for the whole world, a single one for the whole world, an electron-positron collider like SLAC here at Stanford, but much, much, much bigger. And that would be a world machine, with contributions from all the countries involved. And that's still for a number of years ahead.
So, one anecdotal, I wish we could get the U.S. Patent Office to have the hiring...
I'm sorry, what?
I wish we could get the U.S. Patent Office to have the hiring standards of the Swiss Patent Office. But in 2000, Michael Crichton, an author, observed that there were a number of anomalies in physics that were, in theory, going to be explained by simple changes to the standard model and whatnot. And he likened it to the period of physics between the 1890s and early 1900s, where quantum mechanics and all these changes occurred in the way we thought about things. I was wondering...
No, they didn't occur, is what you're trying to say. There were all these contradictions of classical theory, but people didn't take the step of dropping a whole lot of ideas and substituting entirely new ones.
Right.
They did that a couple of decades later.
Right. So I was wondering, in what anomalies? I mean, I read in the late...
I don't know. I don't get my scientific education from this very tall medical student.
What questions do you think will be important to be answered in this couple of decades?
What questions will be answered?
What questions in physics?
Well, I just listed some. Do we really have superparticles? So we have approximate supersymmetry and super Yang-Mills theories, super gauge theories. Do we actually verify all that? Do we get to understand the size of the cosmological constant or whatever replaces it in explaining the acceleration of the expansion of the universe? And what about constructing a unified theory based on superstring ideas? Will that be successful? Will we verify the existence of an actual Higgs particle, one or more Higgs particles, rather than finding some kind of Higgs-like mechanism that doesn't involve a new particle? in order to explain the masses of otherwise massless particles, and so on and so forth. Lots of very well-known questions.
Thank you.
I don't know what this guy has in mind.
Well, somebody has to ask this question. Dr. Robert Bussard was here a few months ago.
Who was?
Robert Bussard.
Oh, really? The
Yeah.
twin person?
I'm sorry?
The twin guy.
The twin guy.
The guy with the twin studies.
No.
Identical
Well,
twins separated.
He may have done
at
that as
birth.
well, but he was here for another reason.
No, this is a different person. Okay, who is it? I don't know who it is.
He was talking about an extension of the Farnsworth containment mechanism for fusion.
The what?
For fusion.
I'm sorry, I just don't understand. I don't know what you're talking about. You're talking about some field to which I'm not, with which I'm not familiar.
Electrostatic containment of fusion.
Pardon?
Electrostatic containment of
fusion. Oh,
fusion.
Containment of plasma?
Yeah.
Containing milk and rubber bands? It's hard.
Well, I was going to ask you if you evaluated his...
I'm sorry. I didn't hear.
I was going to ask you if you had evaluated his work.
I don't know any of this. I'm sorry. I did follow some developments in the attempts to achieve practical thermonuclear fusion some years ago. It's been going on for a long time. It's 56 years, I
Right,
think.
yeah,
The U.S. has been
now.
working on this, and probably a bit longer elsewhere. It was highly classified to begin with in 1951 or so, 52. While it was very highly classified, they had a meeting at Berkeley of people working on various approaches to thermonuclear fusion. And it was held in a movie theater. And the project was called Project Sherwood. People brought pads of paper into the meeting to take notes, but then they had to turn the pads of paper over to security guards as they left, even if they were blank. However, the owner of the theater was a wag, and a wag with access to some knowledge, because the marquee of the theater had 2 movies listed, which weren't playing at all. But the titles were up there: Men of Sherwood and Top Secret.
All right, thanks.
That's all I know. I'm sorry, I don't know about that.
Thank you very much, Dr. Gell-Mann, for your contributions and for your talk here. There's a fine line between being a creative innovator and being a disruptive nuisance. It can be argued that it is equally or more important to communicate persuasively as it is to think creatively. What are your thoughts along these lines?
Oh, I think it's always good to do that, to persuade people. But there's some people whom it's very difficult to persuade. And to waste one's energy on perpetual debate with those people is probably not a good idea. But there are other people who are accessible to reasonable arguments and so on, and one should deal very gently with them and try to persuade them.
Thank you.
Or maybe they're right and you're wrong, in which case you should let them persuade you.
I've read that you have interest in a number of languages.
I'm interested in relationships among languages.
And you
very much so.
speak-
And I have
and
a
you're
project.
fluent in,
I have a project of that kind involving some brilliant Russian linguists.
And you are fluent in 13 or so?
Pardon? No, that's you know, you can't trust things like that. Like,
Is there any interaction between...
I mean, I'm not recommending that you burn all copies of this, but it doesn't contain only things that are true.
Is there any truth at all to that section of the page?
Well, I don't speak languages other than American English correctly. But I know a little bit about languages, and I'm sort of an honorary linguist, maybe, honorary amateur linguist.
Do you
and I'm very interested in the relationships among languages, and I've learned quite a bit as a result. And naturally, I know a few words of various languages as a result. But that I speak correctly some large number of languages is just not true.
Is there any interaction between creative thinking and languages or learning languages that you've come across in your study, in your amateur study? Thank you.
I don't know. I'm not sure. I'm not sure about that. I haven't. I'm not sure whether there's such a connection. Well, I guess that's it. Thank you.